The Millennium Prize asks whether pure Yang-Mills theory on flat four-dimensional space has a positive mass gap. On a flat grid, gauge fluctuations are chaotic, and proving that confinement emerges dynamically remains an unsolved problem. To analyze this, we change the topological background to the Poincaré Homology Sphere, a manifold defined as the quotient space of a hypersphere by the binary icosahedral group, or S3 over 2I. On this manifold, the mass gap depends on the underlying Ricci curvature of the space. Moving to this curved space removes the need for non-perturbative approximations. On curved ground, the mass gap is a solvable mathematical result. This matrix shows the structure of the derivation. It uses three independent mathematical disciplines to deconstruct the mass gap. First, Riemannian geometry establishes the universal existence of the gap. Second, algebraic topology enforces a finite moduli space, isolating exactly three distinct vacua. Third, finite group theory allows for the calculation of the exact mass gap eigenvalues at each of those vacua. These three mathematical domains converge to define the physical reality of the vacuum. This is the gauge covariant Hodge-Laplacian. Derived from the Weitzenböck infinity, it determines the lowest non-zero eigenvalue for spatial gauge fluctuations. The first term is the connection Laplacian. Acting on bundle-valued one-forms, it is positive semi-definite, meaning its minimum value is 0. The second term is the Ricci curvature. For a hypersphere of radius r with a round metric, the Ricci tensor equals exactly 2 over r squared. Adding a positive semi-definite operator to a positive constant forces the entire equation above 0. This establishes a geometric floor. Every gauge fluctuation is bounded above 0 by a minimum eigenvalue of 2 over r squared. This bound is universal. It holds for any quotient inheriting the round metric, regardless of this specific flat connection. The positive Ricci curvature ensures a strictly positive mass gap before performing any further spectral calculations. To understand the structure of this gap, we classify the flat SU2 connections by mapping homomorphisms from the fundamental group 2I. This table maps the classification of the fundamental group 2I. This group contains exactly 3 normal subgroups. These 3 subgroups dictate exactly 3 isolated vacua: the trivial, the standard, and the Galois embeddings. The standard and Galois embeddings define distinct conjugacy classes. Their traces are mathematically distinguished by the golden ratio and its conjugate on order 10 elements. Because 2I is a perfect group, the first cohomology group with real coefficients vanishes. H1 equals 0 at each of these flat connections. The vanishing of H1 means the connections have a positive definite Hessian. There are no continuous moduli connecting these families. Physically, this ensures the absence of massless Goldstone modes that could bridge the sectors. The topological constraints lock the theory into 3 discrete, unbridgeable vacua, 3 vacua corresponding to 3 particle generations. This diagram shows the extended E₈ lattice. We use the McKay correspondence along this graph to find the exact mass gap eigenvalues at each isolated vacuum. On the hypersphere, coexact one-forms organize into descending energy levels, labeled K equals 1, 2, 3, and so on. Physical modes on the quotient space must satisfy a twisted equivariance rule. A vacuum's adjoint representation must explicitly appear in the spin content at a given energy level. If it is absent, that level is filtered out. The standard vacuum corresponds to the adjoint representation 3A. This representation appears immediately at the first level, K equals 1. The eigenvalue formula for P equals 1 yields a standard vacuum gap of exactly 4 over r squared. The Galois vacuum corresponds to the adjoint representation 3B. On the E₈ diagram, this sits at the extreme branch tip, at graph distance 6 from the origin. We evaluate the Galois vacuum at level K equals 1. The mode is filtered out. Level K equals 2, rejected. Level K equals 3, rejected. Level K equals 4, rejected. At level K equals 5, the 3B representation finally appears in the McKay decomposition. This is the first allowed mode for the Galois sector. The eigenvalue formula for K equals 5 yields a gap of 36 over r squared. This creates a ninefold mass enhancement compared to the standard gap. This hierarchy is a topological requirement generated by icosahedral filtering on the E₈ lattice. This chart separates the variables. The gap's existence, the discrete vacua count, and the ninefold enhancement are topological invariants. The lowest eigenvalue scales as 1 over r squared, making the actual magnitude metric dependent and fixed by the cosmological parameter r. This derivation is exact. It relies on finite mathematical computations in group theory and geometry, bypassing the approximations inherent to standard lattice QCD. These are testable physical predictions. This framework can be falsified through lattice measurements on this geometry, verifying the mass scaling and the ninefold Galois enhancement. On flat space, confinement is a dynamical problem that must be approximated. But by evaluating the Yang-Mills problem on this topological background, the mass gap becomes an exact geometric property.